How can I remove this? Okay. Okay, great. It's starting now, I guess. Oh, yes. It should be fine now. Okay, yeah, well, I hope. How to get rid of this bar? Oh, thanks. Oh, you know, Jan? Oh, the more menu. You know how difficult this is for me? I cannot see the arrow when in there. You want to do it? Why do you think that is more? You have this issue?
Because it's not yet. And hide.
Hide? Okay. Okay, this is going to be the hardest today. Okay, yeah, hello everyone. Welcome to this course, Computer Architecture, Master's Degree, ETH Zurich. The main lecturer in this course is Professor Mutlu, Professor Onur Mutlu. I'm going to introduce him in the next slide. He unfortunately cannot be here this week and next week. He's traveling because he has other commitments. And so that's why I'm starting the course. Sorry. My name is Juan Gomez Luna. I work with him as a senior researcher. I'm also a lecturer. So I teach a couple of P&S courses here at ETH as well in the Department of Electrical Engineering. And yeah, I've been working with him for the last 5 years. I'm the lead TA of this course together with Mohammad Sadar. He's not here today, but you will meet him soon. And yeah, also people, I mean, there are a lot of people involved in this course. Yang is one of them. But yeah, in total, we are about 12 or 15 TAs, and we will be usually coming here. I mean, not all of us, of course, but yeah, you will have good chances of interacting with everyone. Of course, you know, when you go to office hours, when you have to solve your homeworks or your labs, etc. Today, as the lecture, I mean, the title of the lecture says, we are going to introduce the course and provide some basics. It's sort of a very general overview of what's the state of the art in computing architecture, what are interesting topics that many of them we work on in our group. From memory systems to compute, I mean, to CPUs, accelerators, and everything, and software, hardware, and all different levels of the stack, as you will see. So let's say that most of the material, or if not all the material that we are going to be covered today, will be covered later in much more detail, right? That's something that you could expect. You can ask any questions. Feel free to ask any questions about anything related to the course, even though tomorrow, where we will go more into the meat, right? We will start talking about the problems of current problems of memory systems, but we will also have a part about the logistics of the course. So even though we will talk about the logistics tomorrow, but also feel free to ask anything that you need an answer right away. Okay, any questions so far? Okay, great. So yeah, this is Professor Mutlu. He is a professor at ETH Zurich since September 2015. He was previously at Carnegie Mellon University teaching, but before that, he did his PhD in UT Austin, and then he worked in several companies, as you can see. Microsoft Research, for example, he was leading the computer architecture research group and really produced some of his best papers. Here you have his contact information. There's everything in his website, talks, papers, etc. Papers, for example, are all here. As you will see even in the slides today, in his website, you can find the papers. You can find slides that the authors use to present that work in a conference, for example, links to recordings and many more things, extended versions, etc. And reach him in his Gmail, probably. That's the thing that he checks the most, and he usually replies quickly. If not, we can also reply if the questions related to the course. I would suggest that you CC me or CC the mailing list, and we will try to provide an answer as soon as possible. If it's something that you think that might be good to know for everyone in the course, it's better that you post it in Moodle, right? In Moodle, we will have Q&A forums. And Professor Mutlu does research and teaching in many things, in computer systems, in particular computer architecture, with a focus on hardware security and also important applications these days, such as bioinformatics. But yeah, all components of the computer architecture, from the memory and the storage, security, safety and predictability, fault tolerance, hardware-software cooperation. We are going to talk about these today as well, how we have to let's say, connect very well all the different layers of the stack. That's what we call hardware-software cooperation, and then different architectures, for example, accelerators for bioinformatics or health or medical applications. And this is, let's say, like what's the key goal of this group? Oh, what is this? Key goal of this group is to build fundamentally better architecture. And this requires us to understand and to work on all the different parts of a computing system. This is why here you see general purpose CPU, you see graphics processing units. You also see, well, maybe this is an accelerator. No, this looks like a CPU core, but maybe FPGAs we could also have here. We have main memory, we have persistent memory and storage. Persistent memory these days is typically non-volatile memories. We are also going to briefly talk about them today. And this previous, let's say, main goal of our research group and also our courses is somehow forks into four current key directions. Fundamentally, secure, reliable, and safe architectures that are also energy efficient and high performance. And examples of them are the memory-centric architectures. You might have heard about processing in memory is something that we work a lot on. But these architectures should be also, if possible, predictable and essentially as well low latency. Well, sometimes we want them to be low latency, sometimes we want them to be high throughput. That depends on what's the actual application, right? And where are we going to use the architecture itself? And then, as I mentioned earlier, architectures for specific applications. In this course, for example, you will learn about our works on acceleration of AI and machine learning workloads, genomics, etc. And the work that we do is traditionally, let's say, placed in this narrow view of the computer architecture that essentially spans the microarchitecture, that is the internal design of the CPU, starting from the logic gates, right, and until you build an ALU or you build a compute data path, and also the hardware-software interface. That's mostly the instruction set architecture. That's the instructions, the commands that you give to the hardware, to the microarchitecture to control it, right? And to make programs work. But in reality, if we really want to have a complete view of computer architecture and something that it's really efficient, we will have to widen this view a little bit. That's what we call the expanded view, and go from the top to the bottom, from the definition of the problem and the algorithm that you're going to apply to solve that problem all the way to the devices and the electrons themselves. We don't work with the electrons themselves, but of course we have to take into account, for example, how much charge we may have in a DRAM cell when we are working on refresh techniques or on techniques to prevent the RowHammer phenomenon, for example. Okay, and another view of all these whole stack from the top, the problem, and also the data that you need to process to the electrons. Yeah, it's all different layers of this stack are important. From the very top where we work on optimizing the software, the algorithms, the hardware architecture, to the bottom. This slide, actually, I think that the figure corresponds to that paper that you see there. There's plenty of room at the top. It's an invitation to researchers, to computer scientists, to look at what we can still do with improving the software, improving the algorithms, and improving the way that we accelerate important workloads. And it's very timely. You can see that it was published 2 years ago, very timely, because this way, these days, as you may know, we are facing somehow the limits of the bottom, right? The limits of the how far the transistors can go, how small they can be, and how fast the circuits themselves can be, right? And that's something that, I mean, people are talking in the last years about the end of the Moore's law. You're probably familiar with Moore's law, right? The scaling of processors, doubling the performance every 2 years. It's something that seems to be closer and closer, not in the end yet, but pretty close. And yeah, that's why that paper was very timely. Same as the paper from which that paper took the inspiration, at least for the title, and probably as well for the, I don't know, the way of facing the problem, is this: there is plenty of room at the bottom. It's a lecture given by Richard Feynman. You might have heard about him. It's his Nobel Prize. And in this interesting talk, I think we have a couple of slides later, he talked about, you know, many new possibilities. This was the late 50s, right? But back then he was already thinking about new possibilities for science, new possibilities for research, and in some way proposed technologies that we already have, such as, for example, nanotechnology, right? So in the end, it's all about analyzing what's the current status, the current state of things, and try to always find solutions for problems that are important and that also might change a lot over time, or might be shaped by, you know, events. Okay. Yeah, this is just to motivate, you know, and from this previous work, plenty of room at the top, things that we can do, for example, with software by simply not changing the hardware, just optimizing the software. And this is a very, say, toy example. What happens if you multiply 2 matrices of that size, 4K in each dimension, pretty large matrices. If you just, you know, write your code in Python, it's going to take about 7 hours. But, you know, there are many different ways of optimizing, starting from more efficient programming languages that are closer to the metal, let's say, that they can generate directly more efficient code. And then different techniques for parallelization or even for vectorization. This is just on a CPU. You see how we can reduce the execution time from 7 hours to less than half a second, right? So, but yeah, this is only for the CPU example. Let's say today we have super fast accelerators, some of them general purpose like GPUs, but also specialized accelerators on specifically this type of operations with matrices. Matrix multiplication is, I would say, the key operation in the current development of AI and machine learning. And indeed, we will see today some of these accelerators. And an axiom for you to take into account, that is also an axiom for our group, to achieve the highest energy efficiency and performance, you must take the expanded view of computer architecture. And what this means is to co-design across the hierarchy from the algorithm to the device and specialize as much as possible within the design goals. If you design a specialized accelerator for matrix multiplication, it will probably be faster than if you do it in the most powerful CPU or even most powerful GPU. And you will be able to do it faster and you will be able to do it saving a lot of energy, right? But that accelerator is only useful, at least in principle, for that particular operation. But also, if you have that accelerator that is super specialized for a specific operation, it will be good that you as engineers, as researchers, think about what else could I do with this accelerator? And not today, but in later lectures, we can show you examples of using accelerators to perform other important operations, such as reduction or such as a scan, prefix sum, or even genomics algorithms on something that has been designed for matrix multiplication. So in the end, the range of possibilities is huge. It's all about, being creative and, of course, working hard. Current research mission and major topics: build fundamentally better architectures. We work, as you already know, or we are talking about the many different directions in computer architecture, data-centric architectures for low energy and high performance. I mentioned earlier processing in memory or processing in DRAM. This is important these days, or it's let's say it's a topic that is getting hot these days. Due to the fact that most real-world workloads are memory-bound. And what that means is that their performance is limited by the access to data, either from memory, either from storage, right? And there are different possible ways of alleviating this bottleneck. And one way that is pretty promising these days is processing in memory. That essentially means providing or enabling compute capabilities in memory or in the storage or in both places. MBMs are also a way of doing processing in memory, as well as a way of having persistent memories that can provide, for example, higher integration. You can have more bits per unit of area, unified memory and storage. Other architectures as well, like low latency and predictable architectures. You should target different problems. Sometimes the problem will have to be solved in real time, right? And that's that would be an accelerator or an implementation that is QoS aware. You have a deadline for a specific task. You need to design the accelerator or the memory or the processor with that in mind. Fundamentally secure, reliable, and safe architectures. That's also, let's say, an important pillar of this course, discussing how to build more secure and safer architectures. We will talk about some problems that you may have in your system due to failures in the microarchitecture of the system. You might have heard about Spectre or Meltdown. In this course, for sure, we will spend quite a bit of time talking about the RowHammer phenomenon. Maybe I will have time to introduce it as well today. I'm not sure if we will have time, but it's not only identifying the problem, it's also proposing a solution. And architectures for ML, AI, genomics, I already said that. And this is also a very interesting direction. And also like a rising trend these days is designing and developing architectures that are data-driven and data-aware. And what this means is that we can improve the computer architectures by understanding well the data that they are going to handle, and by understanding and by analyzing this data. And what I'm trying to say is that AI and machine learning, which are a way of extracting information from raw data, right? We can use that information to make our processors better. Let me give you a very quick example about something that we have published indeed this year at ISCA. You have a storage system, hybrid storage. You have a fast SSD, you have a slow SSD. The fast one typically is more expensive. So typically it will have also smaller capacity, while the other one is slower, but it's cheaper. So you also get more bits per price, right? Per franc. So where do you place the data? Do you place some programs here, or the data for some programs here and for other programs there? Or depending on the phase of the execution of each program, you may want to have your data here or there because you need faster access, or because maybe that memory is more reliable as well, or for many other potential reasons. If you understand the workload and maybe even analyze it on the fly by using a reinforcement learning-based agent, for example, you can make the right data placement decision very quickly, right? And on the fly. So just one example of work we are doing in the group. And this is the logo and the motto of the research group. You also have a link to the website here. These are some of us. In total, I would say more than 40 people these days, including postdocs, PhD students, master students, interns. In the end, whoever wants to work with us is somehow integrated into the group, invited to all our different meetings and even helping, collaborating in projects, depending on what's the interest and what's the level of expertise as well. And as you will see, we do a lot for disseminating what we do, or lectures, research. From time to time, we publish this Safari newsletter. Last one is December 2021. Yeah, you can also find a link there and the other newsletter in our website. And all this work is thanks to people who work in the group and have worked in the group. This is the list of PhD and postdoc alumni of Professor Mutlu. Well, as you can see, yeah, from many different origins and also many different destinations as well. So some of them are teaching these days, or they are in industry as well. I would say the last PhD student to graduate was Minesh. He did his PhD here at ETH and was for several years a TA of this course. And the last two postdocs, Lois and Jisun. Lois is currently the director of the Galicia Supercomputing Center in Spain, and Jisun is an assistant professor at PostTech, yeah, top Korean university. Yeah, you can learn much more about the group in different talks. For example, this one from Professor Mutlu. And also, if you are interested in doing research in the future, or maybe even becoming faculties, yeah, you can probably also get good advice from him. He delivers sometimes lectures of this type, or talks. This one about applying to graduate school and doing impactful research. And also, I mean, probably some of you will end up doing PhD with us, or at ETH in other groups, or maybe somewhere else. You will, I don't know, maybe need some advice on how to apply, or asking for recommendation letters, things like that. We are always open to help you. And teaching is important because teaching drives research. So that's why this course is a lot about talking about our research, and also because yeah, this research in the end impacts other academic research. It impacts research in industry and future developments in industry. And of course, it has to impact teaching as well, because otherwise we would be always explaining things that were proposed and used decades ago. All the materials of this course, but also other courses, talks, etc., are in YouTube, and slides are also linked from there, publicly available. It's a good resource. For example, the good resources as well are those from previous editions of this course and also other courses, right? You have here a link to the playlist of the last year, no, actually first computer architecture digital design course. That's a digital design and computer architecture course in first year of the bachelor's in computer science. This one is the link to the edition of last year. And here you have a few more links for the same one. You see, that's our website. Probably you have already accessed the version of this year. This is the links for digital design and computer architecture. We also have a seminar on computer architecture. That's a different approach. Let's say what we do here is distributing different papers over important topics. Some of them are more recent, others are let's say more classic papers, and students analyze them and present them. It's very good experience for them as well. And this is another more specialized course. This one is about processing in memory. We teach this one as well every semester. These are the links to the last edition, the new edition, the fall semester 2022 is going to start next week. It's a PNS course. I don't know if you're familiar with them. These usually have like 6, 8 students or something like that. Well, let's say that's a maximum number of students that they may have. And they are more hands-on oriented. So it's more like developing your own project. But we also provide lectures because in the end, it's a way of giving you even a better learning experience. Others are about different topics, right? This one, genomics and bioinformatics. We also actually have 2 different courses on bioinformatics. One is acceleration on GPUs, FPGAs, or other accelerators, and the other one is more focused on genomics on mobile and edge devices. This is another one I teach myself on heterogeneous systems. It's mostly focused, as you can see here, on graphics processing units and programming GPUs, usually with CUDA, let's say, is the official language there. But there, most of the lectures are about parallel patterns. Parallel patterns are, compute patterns that can be parallelized in different ways. And in the end, parallel machines might be different by the way that they are built. But there are some, there's some common ground that applies to many different parallel machines. So you can take this as an introduction to parallel computing as well. I talked earlier about hardware-software co-design, about connecting the different layers in the stack. We also, introduce these ideas to some of our students with this course, mostly around research from our group as well. For example, proposals to improve the virtual memory systems, such as this virtual block interface that was the thesis of Nastar and Haji Nazar, former PhD student of the group. A course as well on SSDs and storage. Another one, this is about the FPGA-based exploration of DRAM. I don't know if you have heard about this. SoftNC is a sort of FPGA-based memory controller that allows us to analyze with a lot of detail DRAM chips, different DRAM technologies, play with timing parameters, with refresh, et cetera, et cetera. So it's very good for characterization of real DRAM chips. And also for research in memory systems, RowHammer. Actually, this course, I think it will be a good reference for all of you, because if I'm not wrong, not only because we will cover a lot of memory systems in this course, but also because I think you'll have a lab where you will have to use RowHammer. And this is the whole list and the website of this hands-on project and seminars course. Okay, any questions so far? No? Is it interesting or is it boring? It's a lot of advertisement. No. I'm just introducing, activities in our group for you to get familiar with the group. I think these courses are also all of them very good reference for you in case you want to, get more exposed to some specific topic. We are going to cover processing in memory, for example, here in the next lecture. Actually, not next week. I will give the 2 lectures. One is about processing using memory. The other one is about processing near memory. That are, let's say, the 2 main trends in processing in memory. But then we also have that course. So for many of the works that we will introduce in these 2 lectures, you will find extended lectures there. So that's more or less the reason why I'm presenting them. Yes, they are. Yeah, they are official EDH courses. Yes, of course. I mean, we make all the materials available, and we know that some people follow them from abroad. We even receive messages from time to time, like, "Oh, thank you for the course," or "Thank you for the materials," because people usually appreciate that you make contents available, right? Because in the end, this is just education. But yeah, you can take these courses. I don't know if the P&S courses, if they are only for bachelor, or depends on the department. I try not to understand very well all those issues. But for example, the seminar, for sure, you can take that one. Some students either first do the seminar and then this course, or the other way around. Okay, probably most of you, or all most of you have taken the digital design and computer architecture course, no? Here at ETH. Some of you, right? Okay. No, someone there. Okay. Yeah, so, well, another principle about insight and ideas, focus on insight, on creating insight. Sometimes when you do research, you have an idea in mind and you say, oh, I'm going to implement this, let's say some optimization on a parallel program. And then it turns out that it doesn't work, right? What happens? I mean, it works, produces correct results, but not the improved performance that you expected. What's the problem there? You have to figure out, of course, you should understand what's going wrong. And from that understanding, there is also value that you can provide to others and disseminate. And that's the insight, right? Not everything should always be successful, but many things can be insightful. So that's why it's always good to also encourage new ideas. Don't think that it doesn't make sense to try something. If you have a reason to try it, just try it. Focus as well on learning and scholarship. I think it's very good that you guys have interactions as well with the teaching staff, but also with your fellow students, and focus on learning as much as possible and make this productive for everyone. So for example, if you have a question, you can come in the break and ask me the question, but you can also ask the question right now, because this way you are contributing to everyone's learning, right? And probably others will also have opinions or points of view from which you can also benefit. Okay, in this overall idea of disseminating and educating people all around the world, we also organize these Safari Live seminars. I think that these are usually very interesting talks. I had the opportunity to deliver one of them, but we also have other people from our group, but other people from industry as well, like Jawad, for example, or Dr. Andrew Walker, professors in other universities, more people from the industry. This is one of the co-founders of the Cerebras. You might have heard of these wafer scale ML accelerators. We are going to see, I think, a couple of pictures of them today, and also, different areas as well. Sergey Mangul is a professor of bioinformatics, and we organize them very frequently. This one will be the next one on October 25th, given by Sudamba Gurumurthy, and this one will be about the HBM3 memory. Is a next generation of HBM memories, and yeah, it seems that it has some interesting innovations, right? The HBM memories are widely used these days in FPGAs, in GPUs, and in other accelerators. So this is the newer version. As far as I know, well, not many devices have it right now. As far as I know, the next architecture of NVIDIA GPUs, the Hopper architecture, will use HBM3, providing a bandwidth of up to 3 terabytes per second, something amazing. We'll also have soon a talk by Professor Josipovic. She's a professor here at ETH. And also Christina just graduated. She was PhD student in the National Technical University of Athens, but also a collaborator of our group, part of the Safari research group as well. In the end, we have several papers together, and she graduated a few days ago, and I think she's now joining as a postdoc at the University of Toronto. Okay, it's not only the lectures, the recordings and slides and everything. We also open source all artifacts derived from our research work. These are open source tools you can find in GitHub. Some of them you will use for sure. Ramulator, as I mentioned earlier, but we also have many other simulators. MQSim, for example, is a simulator for SSDs that was also developed here at ETH. The Move and Prim benchmarks are works that we will likely introduce here in the course about how to characterize workloads, to identify what are the different data movement bottlenecks that they have, or Prim benchmarks, that is a benchmark suite for processing in memory architectures. And these are, many more links for the popular or famous RowHammer work, Ramulator, MemSim, Noculator is a network on chip simulator, and many more, right? So as you see, in the end, for essentially every single paper that we write, we generate code, right? Maybe benchmarks, maybe simulator, maybe data, scripts, etc., and everything is publicly available, because it's also a very good way of making your research more impactful. Sometimes we may think, oh, I have developed this, I'm super proud of this program that I developed, and I outperform other implementations or something. I want to keep it for me. Right? It's mine. I will use it for later improvements, and I don't want anyone else to do it earlier than me. That's sometimes a mindset, right, from some people. Well, if you release your code and someone else goes, takes your code, compares, and outperform your work, bravo, right? You get your citation, you get people talking about your work, and also you're contributing in the end to science and the research of other people. So in the end, that's the reason why we believe that it's good to provide people with all these resources. Papers, talks, videos, artifacts. Here you have more links, right? This is the link to the GitHub. And another principle of the group, an environment of freedom, create an environment that values free exploration, openness, collaboration, hard work, creativity. I'm talking about all of these. You will see as well how in the labs, for example, there is a lot of extra credit, because it's not only like, okay, you stay here, you do this, you learn these different steps or these procedures that I'm explaining, but it's also learn by yourself, propose new ideas or new ways of optimizing a memory scheduler, for example. You'll have a lab about memory scheduling, and you can be able, or you are able to try your own scheduling policies, for example. Suggestions to you, these are from Professor Mutlu. Follow your passion. Do not get derailed by naysayers. I think it's important, especially when you are starting with a new idea, right? You go in front of your group and you start explaining, oh, I'm thinking, I have detected this problem. I read this paper and this other paper, and I came up with this idea, or that idea from that paper could be applied here. And someone goes and tells you, no, that's not gonna work, right? You will always hear that in every stage of your life. Those are the naysayers, and they are not bad. They are helping you, because if they ask you those stupid questions, you will find right solutions or right answers to those questions. And this way you will get rid of one problem or one obstacle in your path, right? So in the end, everyone is necessary. Build infrastructure to enable your passion. That's important. In the end, we are engineers. We are not observing the stars, or maybe if you are trying to prove a theorem, mathematical theorem, it might be enough to have a piece of paper and a pencil. But if you are improving computing systems and you cannot fabricate those computing systems because you don't have a fab, in your home, but at least you can create a simulator that can replicate very well how the real system works. So that's why building the infrastructure is important. Or maybe people have created the accelerators or the specialized architectures, but there is no code. There is no there is no people who have tried first to make use of that system. So you can do that as well, right? That's the infrastructure that you need. Work hard to enable your passion and be resilient. I think that also relates to the naysayers, right? Don't get derailed of your ideas, and not only if someone says that they don't like it, also if you make faults and there are mistakes and there are things to improve in your work. Focus on learning and scholarship again, and the quality of your work defines your impact. So always try to do things the best you can. And I think that's a very important principle that also makes a difference. It's not only, for example, how you develop something or how good the results of your work are. It's also how you explain your work to people, how you write a paper, how you create the plots with results or the different graphics that explain how your system works and how different blocks are interconnected, right? So we always careful in all details. So that's in the end the quality of your work, because you can make a good impact on the world. I think that's clear to everyone, and I don't think that I have to explain the many reasons why you can make a good impact on the world if you do your work well. In our area, for example, if you build a system or design a system that is more energy efficient, you will be saving energy, right? Okay, overview talks. These are from Professor Mutlu, many different topics, future computing architectures, in-memory computing, genome analysis, the story of RowHammer. This one is pretty good. I think we may, I don't know if we will have time, but we have some slides from that talk in today's lecture. They will be there because you already have the PowerPoint, right? So you can check them later if we don't have time to cover them all today. Yeah, these are more talks, right? Interviews to Professor Mutlu. I think that one from in NISCA 2019. This one is a speech when he received the Maurice Wilkes Award. More thoughts on DRAM, on how to build an impactful research group. Computer architecture. I think we are going to cover some of these today. I think we are already doing it, right? Why are important computer architectures these days? And also the link to the talk about graduate school. And again, okay, I think this is going to be a required reading. It's transcription of a speech of Richard Hamming from 1986. It's a very inspiring piece. You and your research. I think we have one more slide later. It's pretty interesting, to somehow clear your mindset when targeting research, right? And when getting into research. And I'm talking a lot about research because this course is about research, right? Even if you are not going to do research next year or when you graduate from your master's, but in the end, you also need to learn what research is about. It will be important for your future career for sure. How to approach this course. These are some comments from people, who have taken this course, and the final survey. It's a formative experience. It's high investment, high return. That's important. You'll have to work probably a lot, but you will learn a lot as well. That's why it's a good course. Recorded lectures allowed me to go over the lectures when necessary. That's why it's good to live stream these. The recording will stay there in YouTube for you. YouTube allows me to watch the lectures on my TV. The lecturer is very responsive to questions and remarks from students. Today it's me who's here. Hopefully most of the lectures will be delivered by Professor Mutlu himself. You will see that he's very responsive, but all of us are very responsive. Perhaps even better than in-person classes. That's, I guess that comes from last year or 2 years ago in the middle of the pandemic, because we had to move everything online, but some students at least were pretty happy as well. Easy to understand course format with homework, labs, and lectures. Sometimes you may feel maybe, I don't know, I mean, they will, of course, they will be, of course, everything will be well connected, let's say. But for example, I think you have a lab where you are, I think, or maybe it's the last lab is optional. I think it's about memory coherence. It's not a topic that we are going to cover explicitly in this course, or maybe not, I'm not sure, because sometimes the schedule depends, I mean, it changes a little bit. It's something that has been covered here maybe 2-3 years ago. But even if something in particular is not covered in the lectures, if that happens, is because you already have that background, or that background is going to be provided in a different way. But in the end, doing a lab, for example, about memory coherence allows you to put into practice as well your knowledge about parallel systems that are going to be studied here, about the memory hierarchy that is going to be covered here, et cetera, or even about scheduling mechanisms, or these data-aware and data-aware architectures and data-driven architectures that I mentioned earlier. So if you eventually feel that something is, for some reason, more difficult to you, maybe because you feel that you don't have the background, also come to us, because we can provide the necessary background. That will be probably in the digital design course. Okay, things that we do here, paper reviews. There will be papers for you to review in every single homework, assignments, labs, really a great plan to learn in a comprehensive way. Yeah, this is true. The course was fantastic, and I would do it again at any time. That was my mom. And yeah, it's a good learning experience. It's also a matter of long-term trade-off analysis. So you are going to do an investment now, but in the future, you will see that, you know, all these things that you learn, even if you are, I don't know, programmer or anything else, or in industry, you will see that a lot of the knowledge and understanding coming from this course will be useful. And also, yeah, you'll have to put into practice your critical thinking and decision making. So yeah, let's focus on concepts and ideas, fundamentals, cutting edge technology, and hands-on learning. That's why we have the labs. Your mindset will determine what you get out of the course. Okay, and this is again the talk or the speech from Richard Hamming, and this is actually a couple of paragraphs. This is him. Probably you know about him, or at least you know about some of his works. I think that Hamming distance is known by everyone. We will probably talk about Hamming distance as well in some bioinformatics lecture that we will later have. But yeah, that's an interesting excerpt of the text where he says something like, you need to know yourself, your weaknesses, and your strengths, right? That's useful for research, but I think that's useful everywhere else in life. And you should be able to to make an effect an asset, right? So in some sense, when you know yourself, you can also take advantage even out of your weaknesses. There are some people that are not successful, he says, when doing research, either because they don't work on important problems, or because they don't become emotionally involved. That's, I would say, applicable to many other things in life as well. And they keep saying that it's a matter of luck, right? That's losers always say that. But yeah, get rid of those stale and bad ideas, go forth and become a great scientist. Okay? Remember, we were talking about why this course, why computer architecture, and let's first define what's computer architecture. Is the science and art of designing computing platforms, including hardware, interface, system software, and programming model, and to achieve, in order to achieve a set of design goals. Among these goals, we have highest performance, we have longest battery life, so we have energy efficiency, we have the best average performance across workloads at the best performance and cost ratio, And here is where you see, right, this dichotomy between accelerators, between specialized architectures and more general purpose architectures, right? You may not be able to create an architecture that is the best for every single workload, but you can probably come up with or create or design the best architecture that provides you the best average performance and energy efficiency, and many more things. Or designing a supercomputer is different from designing a smartphone, but some fundamental principles are similar. So many of the things, let's say all the things that we will study in this course can be applied to either supercomputers or the compute units that a smartphone or even smaller devices have. Different platforms, different goals, depending on what's your goal, what's your workload, what's your application. You may want to use something like this or something like that, or maybe you need to use this where you probably also want to have some sort of compute capability. These days, more and more is important to pay attention to optimize edge devices. When we talk about devices working on the edge, we talk about something like this. This is just one example, and today is more and more important to try to also compute and produce some meaningful information here, because that can be really beneficial for the whole system. If this drone is just capturing images and sending complete images, the raw data to some server for the server to process, it will likely spend more energy than by having a small processor there or a small execution unit there that extracts only the important information, gets rid of the images, and just sends the already filtered information, right? So it's just one example. This is another good example: self-driving cars. You may end up needing a whole processor, a whole CPU inside the bucket. This is a supercomputer for sure for a completely different purpose, but many supercomputers these days are used to train machine learning workloads, and later these machine learning workloads are used here, right? So probably you will be doing inference here after training has been done here, or maybe doesn't need to have such a powerful system. Maybe something smaller is also good. It depends on how much data you need to process, for how long you need to train the network, for example. These are supercomputers. This is the, which one? This is the Tianhe 2 from China. This was once the fastest in the world. I think that's this one is the next one is Fugaku. It's a pretty cool picture. Probably you don't want to have that in your living room, but it's pretty useful if you have such a large room. It occupies more or less quite well. Another example platform, that's the tensor processing unit. Have you heard about the Google TPUs? These are used for training and inference of deep neural networks. They were presented in ISCA 2017, and they have somehow revolutionized as well the way we train and the way we do inference in neural networks. But interestingly, if you look at the inner details of this design of this board, you will see that in the end it's not just but a systolic array. And systolic arrays are a sort of processor that were invented back, I think, in the beginning of the 80s, right? So observe also how important ideas that have been proposed in the past and maybe were not so impactful in the past can become really impactful and really useful some years later. And there have been several versions of the Google TPU. This one is the latest one. I think this one is the version 4 from 2021. In every generation, they have doubled essentially the maximum compute power, 250 teraflops versus the previous version. You see 90 teraflops, and and so it's that's per chip, and that's the compute throughput per board. And this is another machine learning accelerator. This one is from Tesla. It's pretty cool because it has these two redundant chips for better safety. That is something that you really need, right, for the specific application that this accelerator is designed for, right? If you have a self-driving car, it's much better if your system is safe. And they keep, let's say, improving their systems, and they recently, I think this is from August this year, they presented this Dojo chip and system for training machine learning workloads. I think it's a very interesting design. As you can see, there are some host CPUs. You can assume that all execution of a program starts here, but at some point, the most important part, and probably the most time-consuming part of the workload will be offloaded to these tiles. Those tiles are composed, as you see, out of 5x5 chips, and we have a later slide about the chips, and observe as well how they have integrated these interesting, let's say, interface processors, I think they call them, with high bandwidth memory and connected to both the CPU host and the host CPU and the accelerators. This is actually a picture of the Dojo interface processor, and this is the chip. Remember, in each of the tiles there are 5x5 of these, right? And pretty powerful by itself, just a single chip. So imagine the whole system, how fast you can train the workloads that are important for Tesla. It's interesting to observe these two different values of teraflops that in the end give us what's the maximum or the theoretical peak throughput or peak performance of the system. It all depends as well on the a specific data type that you use. These 362 are for BF16 and for these CFP8. So 16 and 8-bit representations of decimal numbers, as opposed to the classic floating point 32. There is a float that you're using in C programming, for example, in your CPU. More and more, as you probably know, machine learning workloads and other workloads as well are implemented as much as possible with lower precision because the workload tolerates that. You may know that these neural networks are pretty resilient, pretty robust. So even if you train them or if you use them in inference with a lower precision, they will still produce good results. And at the same time, you can build accelerators that are much more higher performance and save energy as well. And all these developments and all these speed in creating new new accelerators and new systems, it's also because the requirements of the workloads increase. Sorry. Okay. Yeah, it's 2:15. I think I can talk for 15 more minutes and later we can have a break. Is that fine? We will, by the way, finish the lecture maybe 10 or 15 minutes before 4 because today I have a commitment at 4:30 and I have to run. But yeah, we will continue tomorrow. And we still have a lot of time. Yeah. Yeah, exactly. That's how it is. I think it's a really good question at this point. I have already been talking about general purpose or mentioning general purpose processors and accelerators, specialized accelerators, and that's more or less the type of compute unit that you are going to find out there everywhere, right? Either something that is more specialized or something that is more general purpose, right? In the case of the TPU, it's specialized. It's optimized to perform mostly matrix operations, matrix multiplication, matrix vector multiplication, right? Why is that? Because the accelerator is designed for a specific type of workloads that are deep neural networks. if you go to a deep neural network and you analyze how it's implemented for CPU or for a GPU, you will see that most of the layers can be lowered, can be transformed into a matrix multiplication. So that's why if you are targeting, let's say, an important class of applications that are important for multiple reasons, right? Neural networks are everywhere these days, and you want to accelerate them, it might be a good idea that you create a specialized architecture for this specific workload, right? But if you are just, I mean, for example, you just need a cell phone for different reasons why you use a cell phone, and you want to handle these different tasks reasonably well, what you should try to do is optimizing this general purpose processor in a way that can be more or less good at every type of workload, right? You're asking if a TPU is the same as a GPU? Yeah, exactly, because it's more specialized for that, right? So GPUs are as well general purpose. They are good at parallel workloads, especially massively parallel workloads, but you can essentially run a program about anything, right? Or anything on a GPU. The GPU is already quite specialized, but is not as specialized as a TPU that is, let's say, only for matrix multiplication. No, not everything, not everything. So imagine, for example, graph processing. You're familiar with graphs, right? So in graphs, you know that they are typically highly sparse. Graphs are useful to represent users in social media, for example, in a social network, right? And each of us has a profile there, and you have friends, you have connections, right? But not all of us are connected to everyone, or not all of us have the same connections, right? So a way of representing that information is a graph. As you can see, it's highly irregular. It's usually as well, if you say store it in a machine, you will see that it's very sparse. And graphs are normally represented using an adjacency matrix. You have the users here, the users there, and you will have a one wherever you have an edge, connect one or a specific number, wherever you have an edge connecting two users, right, of the graph. So that's very sparse. And you will typically store that with a compressed representation, right? So some of the rows will be like this, some of the rows will be like that, right? And now when it comes to accessing data in that sparse matrix, you will have a lot of irregular accesses, because sometimes you will access, these three elements. One of the elements corresponds to column 0, the other one to column 20, and the other one to column 100, while in the next row, you're going to access completely different columns. So the accesses are very irregular, right? So an architecture that is optimized for matrix multiplication doesn't need to be good at accessing data in an irregular manner. Why is that? Because in matrix multiplication, you either access a whole row or a whole column, right? So it's always contiguous data, right? So the way that you access one in one case or in a different case is completely different. And that requires you to optimize the architecture in a different way, up to the point that there might be some architectures that are not even capable of doing certain operations. If you are designing your accelerator for a highly regular workload, it might not be even able to access two different values. I mean, in the end, you can always access them, because instead of bringing only the value, you bring a large chunk, and then you just use the result for the specific value. I mean, there might always be ways, or in many cases, right? But this is more or less how it is. You were talking about GPUs, and GPUs are especially interesting. Why is that? You're probably all familiar with GPUs since you were kids and were playing games at home in your Xbox or PlayStation, etc. They exist thanks to the GPUs, right? GPUs appeared at some point to accelerate the generation of the graphics for the displays, for you to be able to play your favorite game. But at some point, let's say early 2000s, some people thought, okay, if I have this GPU that has been designed to create an image of a specific size, let's say 1024 times 1500 number of pixels, that's essentially a matrix, right? So why don't I try to just make use of the programming framework that I have to program graphics on this GPU and play with the different APIs that I have or library calls that I have in this programming framework and try to execute a matrix multiplication. And they could do it, right? Because in the end, it's parallel hardware. It has a lot of execution units, small ones. They are all the same, but they are very good at doing certain operations. For example, at reading data that is continuously placed in memory and performing simple operations on each instance of that data, on each element of those arrays. This way you can do a matrix multiplication. At some point, people started to think, okay, yeah, you can do matrix multiplication, but I mean, you are doing it using an API or an interface, a programming interface that has been designed to create graphics. So if you want to use it for general purpose computations, you'll have to change things, right? So some people in university, I don't remember exactly what it was, maybe Stanford, they started to design new programming models, new ways of organizing the underlying architecture to make it general purpose without doing graphics in a good manner as well, right? Because that's essentially was the main goal of these type of processors that are still called graphics processing units these days, right? And there was some academic research proposing that, and the people who proposed that later moved to NVIDIA. Ian Back, for example, he moved to NVIDIA and he created CUDA. And in the year 2006, NVIDIA launched CUDA. They changed some things in the architecture, but they mostly proposed or provided a new way of programming that hardware. That was 2006, 2007. So at that point, many people in academia, more than in industry, said, okay, let's buy one of these G80 that, or GTX, what was it? Well, I don't remember, GTX 8800 or something like that. Let's buy one and let's program it in CUDA. And then they started to show performance improvements of up to 100 compared to the state-of-the-art CPUs, right? So some people started to work on using graphics processing unit for high-performance computing, for example. Until one day, someone said, oh, I have to do a course project. I'm studying, I'm working with a professor who is an expert in machine learning and artificial intelligence, but I'm also taking this course about parallel programming, and I'm learning how to program GPUs, and I have to do a course project. So why don't I try to map one of these networks that my professor teaches to one of these architectures that I'm learning how to program and see what happens. And what happened is that they created AlecNet. That was, we can say, the first deep neural network that essentially changed the world in 2012. And in the last 10 years, we have seen how NVIDIA, because they are smart guys, said, oh, we can keep using our GPUs for gaming and also for HPC, and now supercomputers have GPUs, but turns out that someone has discovered that they are super good at training neural networks. And then they started to invest on improving that capability. And you know what they did? They extended in the year 2017, 5 years after AlecNet, they extended each of the compute units with very specialized units for matrix multiplication. You see? So that's more or less how things evolve. It's a lot of, chance, luck, and also unexpected events. Because these days as well, we put more and more effort on accelerating, for example, genomics workloads. Why is that? Because if you are good at, you're fast at doing sequence alignment, you might be able to do metagenomics, for example. And metagenomics is a branch of bioinformatics that analyzes not a single virus, not a single genome, but all genomes that are at a certain place. And this way, you can identify, for example, where a lethal virus is, right? And that's more and more important. Why? Because we just escaped from a pandemic. So this is more or less how things happen. Are you happy with the question? With the answer? I'm happy with the question, for sure. Thank you. Any other questions? Okay. Okay, yeah, so the neural networks are evolving very quickly. Here you have, in some way, this slide is from Tesla, but here you have, in some way, a simplified view of the computing stack that I showed you earlier, right? Chip, system, cluster, software. And this is another example. Actually, I mentioned already this one. This one is indeed for machine learning. It's the largest machine learning accelerator chip. It's not even one chip, it's one entire wafer. You see that the wafer is divided into tiles, and then in each of the tiles, there are super specialized compute units, SIMD units, that are likely very good for matrix operations, but they also have figured out ways of accelerating sparse matrix computations as well. And you can compare it to the largest GPU in the market right now is the Ampere, NVIDIA Ampere GA100. And it's super powerful GPU. You cannot, I mean, here we are not comparing apples to apples. It's just to show how large is this in terms of area compared to the other one. If you want to go to the equivalent of this Cerebra's wafer scale engine in terms of GPUs, you will probably have to go to multi-GPU systems. NVIDIA has a system that is called DGX, if I recall correctly. It has 8 of these A100. They are connected with high-speed links, and probably, you know, they perform also pretty fast at training or accelerating the same workloads as these Cerebras or similar ones. And I mentioned this, right? I already talked about accelerating genome analysis as well. And we may want to do this in many different ways. We want to do it maybe in a supercomputer, but probably as well in a mobile device. That's why we have one of these P&S courses is about mobile genomics. And this is one that is especially interesting to me because I work with it, is the first real world processing in memory system, or the first compute system that is real world and is publicly available, and you can even buy it, and has processing in memory capabilities. And as you see, essentially consists of a CPU. It's a dual socket CPU. Indeed, you have the two, there you have the two CPUs, and then it has, you know, memory controllers, memory channels, and connected to them a bunch of DIMMs. Some of these DIMMs, as you see, are DRAM memory. They're working as main memory, while some others are compute capable, are what we call the PIM-enabled memory. And actually, you can also see them in the picture. These are the DRAM DIMMs, and these are the ABMEM DIMMs. So this is a real-world system. We work with this system. We have written this paper, but later a couple more papers. And it's very likely that you will have a chance to work with this system in this edition of the course, because we are starting to prepare a lab on how to program this. So I will probably deliver also one specific lecture about this architecture. And probably we will still have time today to see some related slides. Okay, what's a computer architecture? I think this is already clear. The science and art of designing, selecting, and interconnecting hardware components by designing the hardware-software interface to create a computing system that meets functional, performance, energy consumption, cost, and other specific goals, right? That's what we are talking about. Remember that to do so, you need to have an expanded view of the computer architecture, right? Of this transformation hierarchy. And this is a slide that I already mentioned earlier, or toy example about what to do with matrix multiplication, how to accelerate it with different programming models and with different execution units, because in the end, the vectorized execution or the AVX instructions are using specialized SIMD units that are in the same chip as the rest of the CPU. Again, why study computer architecture? Enable better systems, make computers faster, cheaper, smaller, more reliable, enable new applications as well. Also taking the opportunity of using new architectures to enable new applications, as the example of machine learning and GPUs, and enable better solutions to problems. And of course, a goal of this course is understanding why computers work the way they do. Today is a very exciting time to study computer architecture. Industry is facing a large paradigm shift. It's probably something that is happening most of the time, right? Because there are new challenges all the time, and industry needs solutions for these challenges all the time, and also because there are, let's say, non-ending problems, I would say, because there are always things to solve or at least to improve, right? We have day by day, we have more and more data that needs to be analyzed. It's not a new problem. The problem already existed 10 years ago, but now we have much bigger data sets, and we also want to extract information from them. So we need to improve the computing systems to do it better, and at some point to do it in a different way, because there is no, I mean, you cannot go farther with a particular technology or with a particular direction. The science can be or should be more or less complex, depending on what are the specific usages. You will see as well that the type of core that that you have inside a CPU is not the same as you have inside memory in this processing in memory system that I just presented. And yeah, many more problems: memory, reliability, programmability. I think it's very important as well. When you enable a new technology and make it available to people, people should start learning how to use it, right? And 30 years ago, it wasn't so important to be able to program parallel machines, but today GPUs are mainstream, and it's or probably pretty useful for you as computer scientists to know how to program a GPU, or at least know the fundamentals of programming these parallel architectures. And it's not the only thing. There might be, for different reasons, architectures that are especially difficult to program, but it's always possible to provide higher levels of abstraction in the, let's say, programming stack, right? And instead of programming something with assembly instructions, or even in something relatively low level like C, you may be able to develop a programming language and a programming framework that is higher level and can be programmed in a much more efficient way and with fewer lines of code. Okay, but yeah, there is no clear and definitive answers to these problems. That's why we always have to keep working. These problems affect all parts of the computing stack. If we do not change the way we design systems, there are many new demands from the top because there are new problems, new large amounts of data to process, new algorithms to develop, and I just gave the example of the programming and programming languages, and also always new issues at the bottom along the way of improving of all these circuits and logic. And also personalities and demands from users change, right? 30 years ago, we didn't need like super small processors that can operate in your cell phone or in your smartwatch or whatever. So that's all about changing demands and personalities of people. Okay, yeah, and actually I was talking about this, right? The computing landscape is very different from 20 or 10 or 20 years ago. Many changes, up, down, forward, and backwards. Every component and its interfaces, as well as the entire system designs, are being re-examined. So we are working, not only us, but everyone who's working in improving computer architecture, either in industry or in academia, are working in all these different parts of the compute system. Again, our axiom, co-design across the hierarchy from algorithms to devices and specialize as much as possible within the design goals. Okay, yeah, I think this might be a good time to stop. You guys want a break? Okay. Yeah, let's stop here. We can continue in, let's say, 15 minutes or 13 minutes. Is it okay? 13? 15? No, no. That's too much. I'll have to finish earlier, remember. Thank you. Okay, yeah, it should be fine now. Yes. Now this is going to be more difficult. I know. Okay. No? It's okay? Okay. Okay, good. Yeah, this is the, I mean, this is from Wikipedia about this speech from Richard Feynman. And yeah, so this is just to highlight, you know, some of, I mentioned this earlier, some of the things that he somehow proposed that would probably happen in the near future. He talked about nanotechnology, or at least in some way mentioned the idea of nanotechnology, and it's something that it's already out there, just as an example. And here, well, he was particularly interested in the possibilities of denser computer circuitry. We have circuits that are more and more dense these days, memories that are more and more dense. And the fact that they are has a lot of advantages because, for example, you can store more. If we talk about DRAM memories, you can talk more. You can store more bits per unit of area, but that also imposes and creates new problems and new things that we have to solve. The more, the denser is a memory, the smaller will be the DRAM cells. And if they are smaller, they are also more unreliable and more susceptible to errors. For example, RowHammer bit flips. And or he presented, or he mentioned as well this idea, right? The possibility of swallowing the doctor. So as you see, ideas firstly proposed in his speech in the year 1959, but very much in current science and even in the industrial products these days. And this is the other paper, the one from 2020. In this case, there is plenty of room at the top. There are many things doing not, I mean, even if you are reaching a limit in terms of electrons, in terms of devices, in terms of integration, it's always possible to better architect the systems, but also write better compilers, write better software, or design more efficient algorithms. Okay, the axiom revisited, there is plenty of room, both at the top and at the bottom, but much more so when you communicate well and optimize across the top and the bottom. So it's, I think I mentioned this earlier, it's not only about how you design the systems, taking into account as many possible different variables as you may have, but when you present your work as well, you should be efficient, you should be good, you should be clear and communicate well, because this is a way of making more impact and making in the end your work more useful to people as well. So that will be important. For example, even if you are just solving an exam question, it's much nicer if I see something clear, I see something that is well written, well explained, than just, I don't know, a few numbers here, some equation there, and in the end I see some, I don't know, some result that looks good, but I don't know where it's coming from, right? So those are the kind of things to take into account. And as examples of cross-layer designs, because I mean, we talk about hardware software, we talk about hardware software cooperation, but there are many different examples for that we will show over the course of this semester. And yeah, let me give you just go very quickly over some of them. IEDM, it's an idea to optimize, make more energy efficient and higher performance deep neural networks, or inference of deep neural networks. And the idea is to use what this paper calls approximate DRAM, which in the end is a way of operating DRAM that produces some errors, but at the same time allows you to save a lot of execution cycles and save energy. Because even if your DRAM is not going to be so reliable, and sometimes the bits flip, and where you had 1, then you suddenly have 0, and that in reality is an error, but probably that error, in many cases, that error is not going to be let's say, harmful enough to make that your system doesn't work, right? And deep neural networks and machine learning are especially robust algorithms. In the end, even when they are trained with many different types of data. Even they are sometimes even noise is injected into the data sets to make the trained neural networks more robust. That's why you can also take advantage of these kind of techniques that accelerate performance and also provide energy benefits. Another nice example, completely different idea of hardware-software co-design is SMASH. It's an accelerator for sparse matrix operations. In this work, we optimize sparse matrix computation, and sparse matrix vector computation by designing new hardware, by designing as well new ways of compressing these matrices. You might have heard, or you might be familiar with COO compression format, or CSR compute. How is it called? Column sparse row. But yeah, those are highly widely used and conventional matrix compression formats. Here we propose something different that is based on bitmaps. But then there is also a software layer to allow programmers to access those bitmaps in an efficient way and later perform the matrix operation. So it's an example of hardware-software co-design. Or this one as well is hardware-software co-design, or even hardware algorithm co-design, because Genome proposes a new algorithm for genome sequence alignment, and also an accelerator that is specifically designed to accelerate this algorithm. Or this one, for example, is not a specialized accelerator, it's a specialized accelerator that is created on an FPGA, right? And in this case, it's a stencil accelerator for weather prediction modeling, and yeah, using high bandwidth memory as well. So that's why we call it near high bandwidth memory, because it's an accelerator created synthesized on an FPGA that is connected to an HVM memory. This is another example, in this case, an accelerator, near data accelerator as well for time series analysis. Time series are useful in many different domains. Bioinformatics is one of them. Earthquake detection is another one. In medical applications, for example, to control the rhythm of the heart of a patient, for example. So widely applicable work as well. This is a newer version of the FPGA work. In this one, it's not only the weather prediction application, also some bioinformatics algorithm as well. If you want to learn about bioinformatics, for sure you will have at least one lecture about bioinformatics, but we are also writing some good papers summarizing more or less the evolution of sequence alignment algorithms and many different algorithms and applications used in this area. This is a very nice review of these works by Mohammed Alser, who is another senior researcher in the group. You will meet him soon. This is one of the original proposals in processing in memory. In this case, is what we call a quartz grain accelerator. You could compare this to a GPU, something relatively large, right? But in this case, this accelerator is optimized for parallel graph processing. I like this work a lot. I mean, it was presented, as you see, 7 years ago, more than 7 years ago. But I like this work a lot because it's, I would say, one of the classic works in the recent research in processing in memory, and it has impacted a lot of more recent publications. This one as well, it's something very interesting study. It's not only because it's about processing in memory and characterizing data movement bottlenecks, also because it's about Google consumer workloads. Amir Ali, who was a PhD student of Professor Mutlu, he did an internship at Google, and he had the chance to work with workloads that we use, or most of us use every day, like Google Chrome or BP9, that is the video encoder that Google uses. mobile TensorFlow, that is what Google uses in their edge devices for machine learning, and a few more, right? And was very interesting study because it revealed many of the current issues that these workloads face in mobile devices these days, or consumer devices, and proposes solutions as well. This one is a little bit older, but it's interesting also to present it or to talk very briefly about it. We talk about processing in memory, right, as a way of alleviating data movement bottleneck, the need to access data all the time from memory or from storage. Remember that earlier we were talking about regular memory accesses or irregular memory accesses. Whenever you have irregular memory accesses, the CPU will struggle in most of the times to get the data on time to feed the compute units, to feed the ALUs, right? And that's especially bad wherever you have pointer chasing applications where you need to read some particular input in a linked list, for an entry in a linked list, and then you have to check the pointer that goes to the next element in the linked list. All of this generates a lot of irregular memory accesses. Processing in memory can be a way of alleviating that, essentially because you are doing the computation closer to the memory, right? So in the end, the burden is smaller. This one is also super interesting thing. It's like a case for richer cross-layer abstractions, bridging the semantic gap with expressive memory. What does it mean, expressive memory? So we are talking here about more general purpose processors. We are talking here about more specialized processors. And we can also talk about the different units that you have inside a CPU or in your computer to perform specific operations that can be sometimes good for workloads, sometimes not that good, right? You are probably all familiar with the memory hierarchy. You know that there is a main memory, and closer to the processor, we typically have cache memories, we have registers, and you might have heard as well of a technique that is called prefetching, for example. What is prefetching? When the processor accesses data or needs to access data, in reality, the processor reads the closest level, and this closest level is typically the L1 data cache, right? But where the data resides originally is in DRAM. You want the processor to have the ability to access data as quickly as possible, right? So you want the processor to always find data in L1, if that's possible, because otherwise you'll have to go to DRAM, bring the cache line to the L1, and that will take probably hundreds of cycles of the execution, right? So there are specific mechanisms in the processor and specific units that are in charge of bringing the data in advance so that when the processor needs one specific value, the corresponding cache line is already in the L1 cache. Is that always going to work well? It will depend on the type of memory accesses that you have, of course, but prefetchers have improved a lot over time, and there are prefetchers that are specialized for different workloads. That could be one example here. But now, which one of the prefetchers want I to work? Well, I'm the programmer, I'm the user, so I probably know my workload well. If I know my workload well, I could be able to provide the hardware with hints about what I want to prefetch, right? Depending on what are the specific needs of my application. So this idea of having the programmer using instructions to provide information to the hardware is what we call the cross-layer abstractions. And they can be pretty useful for many different workloads. These are some preliminary ideas, preliminary ways of implementing these cross-layer abstractions, but for sure, very interesting work that is also creating some impact. And here you have, more or less an illustration of what I just said, right? You have different data structures, code optimizations, access patterns, data types in your program. You know your program. you can somehow provide that information to the hardware in terms of, in order for the hardware to be more efficient. And here you have another, another view of more or less the same thing. And these are some example optimizations that can be enabled or can be activated using Xmen, or could at least be. And in this paper, we show how to do that. And there is at least a couple of follow-up works. This is one of them, indeed. This one applies to GPUs. It's more focused on locality. If you have ever programmed a GPU, you probably know that same as in a CPU is the cache memory, the cache hierarchy, that it's somehow user transparent, right? It automatically does it is able to bring cache lines to the cache and then evict them whenever are needed. In GPUs is not the case for at least all types of memory structures that they have. But you as a programmer should be very careful about how you place data, right? Because there are large register files that are very close to the processor, and you want to use, or very close to the, in the end, in the compute units, and you want to use, but there are also on-chip memories with certain characteristics. So a way of exploiting the locality in the applications and making good use of all these different memory spaces is something quite challenging, but there might be simpler ways by providing the hardware with hints on how to access data in order to better exploit locality. Another example, this one is related to heterogeneous memories and reliability. I think that here the idea is you have different types of data in your application or in different applications. Part of the data will be more vulnerable, part of the data will be more tolerant to errors, to bit flips, for example. Well, depending on the specific needs of your data, you're going to use more or less reliable memories, right? So you could eventually imagine, we talked in a few slides ago, we talked about IEDM, right? About this memory that you trick somehow in order to make it faster and more energy efficient, but that will cause some error. Well, that's probably your tolerant data, right? It can probably be trained using that memory, while other data that is more vulnerable, that you really want to keep the whole of its integrity, you will use it in a more reliable memory. Okay, yeah. And here you see, a little bit more about how to, how to characterize and classify. That's the first step in this work. Characterize and classify the application memory in order to also see how much, so the data in order to see how much tolerance to errors they have, and then based on that perform the corresponding mapping. And this is a work that I already mentioned in the beginning of today's lecture. The virtual block interface is a complete redesign of the virtual memory in computing systems, proposing also, because most of the, let's say, virtual memory handling is done by the OS these days. What BVI proposes is to offload part of that responsibility to the memory controller. This way, have much more efficiency and much more adaptability as well for different environments, like virtualized environments in cloud systems or systems with heterogeneous memories as well. You have a couple of at least a couple of good use cases in the paper. But many more interesting things are happening today in computer architecture. For example, in terms of performance and energy efficiency. This is a very good example of technology that was proposed many years ago, and there was a lot of research in terms of hardware and architecture about this type of memory, and in the end, someday it became real. The first non-volatile main memory produced by Intel. You might have heard of this 3DX Point, or Intel Optane, I think is the commercial brand. And yeah, it's a replacement, potential replacement for DRAM in computing systems. It's a little bit slower, but it has significantly higher capacity than DRAM. So that's one of its advantages. And as a good example of how the research in computer architecture in the end ends up impacting the real world and the real computing systems, this is a paper that was written 10 years earlier by Professor Mutlu and his collaborators, architecting phase change memory as a scalable DRAM alternative. And the Intel Optane is essentially phase change memory. So probably many of the insights of this work have somehow been applied to the existing Intel Optane memories. Indeed, it's something that it has been recently recognized. As you see, they got for this paper some prize this year. So it's something that is being recognized by the industry as well as some impactful research. And this is another version of the previous paper. This is one maybe shorter one, probably also easier to read because it's in IEEE micro, and they usually have shorter papers and more like magazine style. This is something that you have already seen. As you see it, this part of the lecture is mostly about introducing different innovations that we can find in recent computer architectures, right? This is the wafer scale engine. I mentioned earlier as well the talk, the seminar that Sean Lee delivered at some of the Safari seminars. He presented the architecture, and it was super interesting talk. The talk is also available. I think it indeed was, I don't remember exactly, I think it was in February this year. This is the newer version from 2021 with more transistors, more compute power as well. This is another view of the ABMEM processing in memory system that I presented earlier. These are the ABMEM DIMMs. As you see, they look like conventional DRAM DIMMs, right? They are DDR4 DIMMs. The only difference is that in each of these chips, we not only have memory arrays, DRAM arrays of DRAM cells, but also small processors. These processors are called DPUs, or DRAM processing units. And here you have another view, another picture. And yeah, you also know this one. You also know this one as well. This is about a talk I delivered last week with a couple of links to the paper. Well, actually, we have two versions of the paper. One is shorter, the other one is longer. This is a shorter one. And in this work, this is essentially what we did, right? Benchmarking the system, understanding it, not only from the architectural perspective, but also from the software perspective, from the workload suitability perspective. That's important, right? Because maybe you are right now thinking, okay, now sounds like very fancy, these chips, and inside the chips you have small processors, but how do you use it now? Is it good for every single workload? Is it also good for matrix multiplication, for example, or for something more irregular like graph processing? That's what we wanted to figure out, right? We wanted to understand that. And that's why we work with it, not only in understanding the architecture itself, the pipeline, the peak throughput or peak bandwidth that these DPUs can achieve, but also implementing different workloads, like you see, matrix vector multiplication, pretty regular thing, very related to matrix, essentially the same as matrix multiplication, but also with sparse data. Also, databases, select and unique, are simple workloads in the sense that you have to go through a bunch of data, right? And maybe a key value store array, and but you have to go over the whole data. Why is that? Because you need to analyze, for example, retrieve results with people who have blue eyes. So you have to go and check, does this entry has blue eyes, this person has blue eyes, or this value is even value, or this value is greater than 25 or whatever, right? The amount of computation is pretty lightweight in most of the cases, but there is a lot of data movement because if you do this on a CPU or on a GPU, you need to read the whole thing into the into your memory, into your registers, and then perform some simple calculation, right? So that was like very good candidate from the beginning to for this type of architecture. In other cases, we discovered that even though they were like very, say, memory bound with regular accesses and so on, for example, this breadth-first search or the binary search, for example, we realized as well that this system could also not perform even better because it has also its own limitations. So that's important as well to understand what are the limitations of a new system as well. And these are, well, this is the link to the repository. This is title of the paper again, another talk, another one, or maybe the same one. This one is a different one for sure. Multiple versions. This one is 21 minutes. And more works. I think I already mentioned this one, FPGA-based near memory acceleration. Observe that sounds kind of similar to processing in memory. Instead of saying processing in memory, we are saying near memory. Well, in this case, we call it near memory because it's an FPGA. This type of FPGA uses an HBM memory, and these HBM memories have the advantage that they have, like, let's say, like super wide bus. And because you have very wide bus with a lot of lines to bring bits to the FPGA, we say that we are near the memory, very close to the memory. This specialized memory that is connected through it's called silicon interposer, because in the end it's fine, very fine-grained memory bus built in silicon that connects the FPGA and the memory. You can achieve much higher bandwidth here. But it's not also the only type of processing in memory or the only type of near memory processing, and also not the only one in the real world. We got super excited last year when Samsung announced this FinDRAM, their function in memory DRAM, their new processing in memory architecture, bringing powerful AI computing capabilities inside the memory. It's indeed HBM memory, this high bandwidth memory that I just mentioned that some FPGAs have. This HBM memory is in the end a 3D stack memory. As you see, there is this buffer die that is logic, and then there are several layers of DRAM memory, and this is essentially the way of creating a memory organization that is high bandwidth. But the interesting thing of this FinDRAM from Samsung is that they modified some of these layers to integrate small processors inside the layers. Actually, I have the slide here where you see this is the picture of the chip implementation of one of the layers. As you see, the memory or the memory layer is divided into pseudo channels. There are in total, there are actually four no, in this figure. But in each of the pseudo channels, you can identify the cell arrays. So these are the DRAM cells here and here, and in between they have replaced existing logic or existing even more. So they in the end have to reduce the size of the cell arrays in order to place these PCU blocks. And these PCU blocks are essentially compute units that can perform very fast. This is a view of one of these PCUs, or one of these compute units. What they in the end have is are some registers, but then they have a pipeline, and a pipeline in some sense similar to another processor, where you have some unit that reads instructions, decodes them, and sends signals to the execution units, in this case, array of multipliers, an array of others. And why is that? Multiplication and addition, because multiplication and addition are necessary for matrix multiplication or for matrix vector multiplication, and this architecture is specialized on machine learning inference, right? So it makes perfect sense that these PCU blocks are specialized for that. Can we do something completely different? We could probably do more operations than the ones that were initially in mind of Samsung engineers and researchers when they designed the system. It's all about how creative we are in taking advantage of this system, right? But it's not specifically designed for different types of workloads, right? It's specifically designed for machine learning and artificial intelligence. And it's good at that. For that reason, it's also simpler, the instruction set that it has, right? Here, we have a table with the ISA, addition, multiplication, or also fuse, multiply, accumulate that perform a multiplication and addition basically in one cycle in terms of throughput, then some data movement instructions and some jump instructions as well to repeat, to loop over some code, etc. This is the picture you saw earlier. And this is another one, a different proposal, completely different proposal as well from Samsung. Here, instead of modifying the DRAM chip, instead of modifying these layers of the HBM memory to place there some compute units, what they did was changing the design of the DIMM, or at least the design of this buffer that some DIMMs have, in order to include some reconfigurable hardware. For example, an FPGA. Here on the right-hand side, what you see is a picture of the prototype that these are basically two DIMMs with 2 ranks each, and inside, on top of the DIMM, what you have is one FPGA. You can program that FPGA for a specific application. In their first paper, they tested a recommendation system. Another more recent proposal, this one is from another major DRAM vendor, SK Hynix. This one is called Accelerator in Memory. As you can see, it's pretty similar, conceptually similar to the proposal from Samsung, from FIM DRAM. But in this case, instead of having one processing unit per every 2 banks, here we have one per bank, as you see, these PUs. I think, yeah, I have a picture of the PUs in the next slide, right? Interesting difference as well. This one is not HBM memory, but is also another memory, type of memory that is widely used by GPUs these days, is GDDR6. And in the end, because they are as well targeting the same type of workloads and the same type of devices as well. I mean, this might be for CPUs, might be for GPUs as well, but probably more GPUs, because GPUs are even more used for machine learning training and inference. And GDDR6 is a memory for graphics. But yeah, in the end, the interesting part here is how their chip is designed, and then how internally it's architecturally designed. You see, the processing units are kind of similar thing to what we saw in FinDRAM. They have an array of multipliers, and later they have an other tree, because that's what you need to perform a dot product operation, right? To multiply a column by a row, you need to first perform the multiplication and then accumulate all the partial values, right? So that's what you can do with this accumulator. And they even have a few innovations that I like a lot. For example, some interpolation function, and also a way of accessing, obtaining values for activation functions. You might know that many DRAM layers have, some activation function at the end, things like sigmoid or relu or GELU or other type of activation functions. These sometimes require very specialized units. Sigmoid, for example, is a exponentiation, right? And as you see, there is no unit to perform exponentiation there. But something pretty interesting that they do is like creating some sort of lookup tables here in some of the rows of these DRAM banks. And with this unit, they access the exact value that they need from the lookup table, right? So it's a pretty nice innovation as well. Of course, doesn't mean that they are inventing the concept of lookup tables or memorization or accessing data or partial results from memory. Of course not, but they are applying it in a smart way and a nice way. And another thing they have as well is this global buffer that is not DRAM, is SRAM, and it's useful to move data from one bank to another bank. And that's indeed something I believe pretty useful for processing in memory systems, because otherwise you have to move the data. Even if you want to move it from here to here, you'll have to do it all the way over the CPU, which is, as you can imagine, very costly. Okay, one more, also from this year. This one was presented in February, and it's from Alibaba. This is it's even more specialized, as you can see. This one is for recommendation systems, and they nicely describe in their paper what's the basic structure or different stages of a recommendation system. And because they know that, they create some engines that are specialized for different steps, like, for example, the match step, or yeah, I don't remember exactly the name of the second step, but it's executed in this neural engine that in reality runs a small DNN. And here you have a view of the cross section of the whole thing with the substrate, the logic die, and the DRAM die, because it's a kind of I don't know how old is this hybrid bonding. Probably is not very old. Essentially, the idea is fabricating the layer with logic, the layer with the accelerator on one hand, and the other hand, what you do is creating the DRAM die, and then you bond them with the specialized hybrid bonding technology. And this way you have, let's say, full bandwidth, right, between DRAM and logic without having to go through an external off-chip memory bus or something like that. So that's why we call it processing in memory. It's a way of doing processing in memory as well. We're going to learn a lot. You are going to learn a lot about processing in memory in this course. In fact, we are going to talk about processing in memory in the next two lectures, and you will see, or now you see that, and I mentioned it earlier, we divide processing in memory into two main categories. No, I think I didn't say it yet, but I'm saying it now. There are two different categories of processing in memory. One, we call it processing near memory. Near memory, why? Because what we are doing is placing some sort of compute capability near the memory. And if you look at the previous designs, it's exactly what they do, right? Both AppMem, Samsung, SK Hynix, Alibaba, they are designing an accelerator or a processor or a SIMD unit, more or less specialized, and they put it near the memory array, right? I would say that even more fascinating is processing using memory. What do you do in processing using memory? You use directly the memory cells to perform computation. And I'm going to give you a very simple example that is, let's say, the basic idea in what we call processing using DRAM. Is a trend that somehow was first proposed by one PhD student of our group, Vivek, back in, I would say, 2015 or something like that. He published one short paper first, then a longer paper in Micro 2017. And he thought about a very, very basic idea. You guys know how DRAM is composed from inside, right? So if you think about that DRAM subarray, what you see is a bunch of rows. And these rows are, I mean, they are connected to a word line, and this word line has the ability to activate the access transistors that provide access to the charge that resides in, or is stored in the DRAM cells, that in the end are a capacitor. Or one DRAM cell is composed by a capacitor and this access transistor, right? The way that you normally access DRAM is by activating the whole row, and this row gets moved to the sense amplifier, or in other words, when you activate the sense amplifier, when you activate the row buffer, each of the sense amplifiers in the row buffer somehow sends the variation in the bit line charge, and they amplify that. And that amplification might be in one direction or the other direction. It might be 1 or it might be 0, right? And this way you read the contents of the whole row that will be maybe 1, 1, 1, 0, 0, 1, 1, 1, etc. And each of these bits is coming from a different bit line, right? That's the way DRAM works. It's for sure something we will review as well in this course. But now think about a single bit line. how many DRAM cells you have in every single bit line? You may have 1024, for example. You have a lot. And in each of these cells, you're going to store a bit. The operation that I just described is the basic DRAM operation, is opening a row. It's for one single row, but for only one cell in each bit line, right? And when you read it, it might be 1 or might be 0. What happens if you activate at the same time more than one bit line, more than one row? In each bit line, you're going to activate either 2 cells or 3 cells or 4 cells, or assuming that you can randomly choose the number you want, right? But let's say we activate 3 rows at the same time. What are the possible contents of these 3 rows? In total, they have 8 possible variations of contents, right? Let's think, for example, about 2 1s and 1 0. What do you think that the sense amplifier is going to read if I have 2 1s and 1 0? Why? Because in some sense, 2 of the cells are sending their charge to the bit line in some direction, while the other one is doing it in the other direction. So in the end, this is 2 against 1. So who wins? The majority of them, right? If you have 2 zeros and 1 1, the result very likely will be 0. This is called a majority function, and it's a type of logic function. Maybe you don't heard about it in your first digital design lecture, where normally and, or, not are introduced, and later XOR, XNOR, etc. Majority is also a logic function. And you for sure remember and know that with and, or, and not, you have a functionally complete set. And what that means is with and, or, and not, you can create any other function, an addition, a multiplication, a division, a floating point operation. You can do everything with just and, or, and not. Interestingly, you can do also everything with majority and not. So after coming out with this idea of activating 3 rows to perform a majority operation, Vivek also thought about how to do not inside the DRAM subarray. And thanks to that, you can, at least in theory, there are no real-world products yet, but you can have a very large array that operates independently on each of the bit lines, and each of them can be seen as a SIM delaying, as a small processor in some way, right? So that's something you will learn about actually in the next lecture. Not the next lecture, next week on Thursday. That's a type of processing using memory, and it's not the only way. It's not, DRAM is not the only memory that is capable to do that. Some people have shown that this is doable in SRAM as well, in non-volatile memories, or even in flash memory, in a recent work that we are going to present next week, and probably I will also have here. Okay, any questions? Okay, yeah, this is a scalable processing in memory accelerator for parallel graph processing. I talked about this one earlier. This is another one from the same year, same conference as well, completely different approach. Here, instead of creating a coarse-grained accelerator that is very good at something like graph processing, this idea is simpler because it's like, okay, let's detect some few instructions, only a few instructions, maybe an atomic addition, maybe hash table query, relatively simple operations, or a distance calculation, something like that. And let's create a small specialized unit for this instruction, for this operation inside the memory, right? And this way it can be, in some sense, more general purpose, because it can be good for different domains as well. Not completely general purpose, because you can only execute a few instructions there, but can be useful for many different applications. And in some sense, if you think as well about SK Hynix and Samsung proposals, where they are just placing there an array of multipliers and then a reduction tree or something similar, it's in some sense a type of PIM-enabled instruction, right? Because it's a very specialized hardware, very specialized operation. I also mentioned this one earlier, proposing as well near memory processing ideas, in this case, 3-stack memory, but instead of placing small compute units in the memory layers, the idea is to place them in the bottom layer, in the logic layer that 3-stack memories have. And yeah, those are, let's say that the acceleration works by themselves. It's like, okay, we have this workload, I want to accelerate this workload, and this is the processing in memory architecture that I create for it. But there are many more things to worry about when you are trying to enable a new technology in computing systems. For example, you have multiple memory chips, and in each memory chip you have several of these small processors, right? And these small processors, each of them is going to run maybe one thread or maybe several threads of execution, but your program in reality needs thousands of threads or even many more, right? Tens of thousands or hundreds of thousands, as we can find in GPUs these days when we write CUDA programs, for example. So you need to communicate and synchronize all these different threads and different cores. So it's also important to investigate, to do research in efficient synchronization techniques, efficient synchronization support for near data processing architectures or processing in memory architectures, right? And maybe the ideas that you explore and start trying are traditional ideas of synchronization mechanisms in other type of environments, for example, multiprocessor systems, clusters, etc. Because in the end, it's going to be more or less the same, but at a different scale, right? For sure, you will have new challenges that you need to face as well and find specific solutions for these challenges because the environment is completely different. We talk about CPUs, we talk about GPUs. The previous proposals can be good for CPUs as well, but this one is specific for GPU systems. This transparent offloading and mapping work, this Tom paper, that it's about analyzing general purpose GPU workloads from benchmark suites, popular benchmark suites in the GPU community, and identifying in which of these workloads there are parts of the execution that could benefit from some sort of processing in memory by, in the end, creating, you can see them as small GPUs inside the memory. And this is the, I mentioned, I talked about this one earlier, pointer chasing. This is the move, an analysis methodology and workload characterization methodology of real-world workloads to identify different types of data movement bottlenecks, and also based on that, propose different ways of doing processing in memory or using other techniques, for example, prefetching, for example, better caching policies, etc. In the end, it's more like, instead of proposing new hardware here, what we are doing here is analyzing workloads, creating a framework to analyze workloads, and based on that, or based on the results of this framework, the outputs of this framework, to figure out what type of solution might be better for some specific workload. It's also open source, and yeah, these are links to the paper, PowerPoint, video, etc. And processing using memory. Okay, this is the work I mentioned earlier from Vivek, presented in Micros 2017. The idea, basic idea of activating 3 rows at the same time to perform a majority operation is called Ambit. This is another version of that work. This is an extension we worked on last year, presented last year in DRAM. Let's say that Ambit proposes the basic idea, use, create or execute majority operations inside the DRAM subarray. What we do here is really architecting around this idea in order to provide a way of creating, let's say, any type of operation that you may want to execute inside DRAM. Not any. At the moment, this doesn't support floating point computation, for example, but it supports pretty much everything for integers. Even control flow instructions, if you need to do, like different paths for different lanes. Of course, it's not going to be the most efficient thing, but there are ways of doing so as well. All these two works, actually, I would say that the original idea is not from the Ambit paper. It comes from even earlier, starting to do something useful inside DRAM by just playing with DRAM cells. This idea of row clone that for sure we will cover in detail next week is basically opens one entire row, moves it to the row buffer, to the array of sense amplifiers, and then by activating another row and writing, it essentially copies from one row to another row, the entire row. If you try to do that in a conventional system these days, you won't be able because it's basically not enabled, but it's not impossible. There are people in another university, in another group, who have even shown how to do this operation in real chips that you can buy in the market. So it's not that far. In your current CPU, your current cell phone, etc., if you want to perform this operation, you will have to bring the whole row, let's say 8 kilobytes or 4 kilobytes of data, bring them to the CPU all the way through the cache hierarchy, and then write them back to another row in the maybe even in the same DRAM subarray. So imagine what's the large amount of performance improvement and energy savings that this can provide. This is a related technique. In this case, is to send these entire rows farther away. So it's like copy from one subarray to another subarray. And this is even more sophisticated. This moves data inside memory in a more fine-grained manner by, in this case, using global row buffers that are external to the DRAM subarrays. And there is a, let's say, one global row buffer per bank. So by using these, you can do fine-grained data movement inside a DRAM bank. This is even more sophisticated. In this case, it's creating a network in the logic layer of a 3D stack memory. Some of these works, we will cover them in more detail. I think that next week, after we go in more detail, step by step, over the key important works here, you will also understand much faster more details of other works as well. And inside DRAM, we can also somehow compute, not only with the Ambit idea, with the majority functions, but you can also create data that is useful. For example, physically unclonable functions that are pretty useful to identify devices, or random numbers. In DRange, the basic idea is to play with the DRAM internal timings and the way that we access rows. And by accessing them in a, let's say, weird manner, we are able to generate random numbers. We will for sure cover in detail this as well. It's pretty useful that you have a source of true random numbers or you can have it in a computing system, right? It can be very useful for, I mean, it's relatively easy to do, as you will see, or at least conceptually easy to do. But also it's very useful, or can be very useful in computing systems. To have a true random number generator can be used for security applications, encryption, etc., etc. This is another proposal. And this one was somehow inspired by the Ambit work as well. Ambit is we activate 3 rows, we obtain a majority function. And probably most of you have thought here, okay, what if you don't activate 3, you activate 2 or activate 4? Right? Well, in this one, we activate 4. If we activate 4, because it's 2, maybe 2 zeros and 2 ones, it's more unpredictable what's going to be the final result, right? And this allows us to generate random numbers. So it's also useful to, or can also be useful to activate an even number of rows. And this is, this is an extension of the to random number generation. But in this case, it's an end-to-end system design. That's also something normal. You start with some basic idea, let's activate 4 rows at the same time. But after that, you want to integrate that into the actual system and use it on a real world application, right? So this is a demonstration of that. This one is super recent. It's going to be presented next week. I mentioned this one to you earlier. This started as a semester project of one master student who took this course. and it has, well, in the end, is published it's going to be presented in Micro 2022. It's all around this idea of doing computation using DRAM, but in this case, proposing a very smart way of implementing lookup tables inside the DRAM and querying lookup tables in a massively parallel manner inside the DRAM. So as you see, I also talk about lookup tables when I presented the AIM architecture from SK Hynix. We were working on this even before that. And so I think that the publication from SK Hynix, the later prototype from SK Hynix, shows that we were in the right direction when working on this. But in reality, this is even more complex. It allows you to use a whole DRAM or the whole DRAM subarrays at least as lookup tables, larger ones, and perform more, let's say, bigger range of operations as well. And this is also very recent one. Flash Cosmos is similar to the Ambit idea, the idea of doing bitwise operations inside memory, but in this case, it's done in NAND flash memory. So now we not only have potentially the ability of do computation using DRAM, now we can also do it potentially with the storage. And imagine in the long term, what are the benefits that may have, right? Because until now we had the data in the storage in an SSD, and we had to bring the data to memory, and then from memory, bring it to the processor for the processor to compute. We are enabling ways of doing computation in memory, so now we don't have to go to the processor, we don't have to bring the data to the processor, but maybe at some point in the near future, we will be able to do the computation directly in the storage. In fact, there are indeed some commercial products that already do some sort of computation in the storage, but they are using FPGAs there. It's not like this thing that is more with the NAND flash cells themselves. Okay, yeah, well, I think this serves as an introduction to processing in memory. This is recommended reading for sure for all of you, especially if you want to do research in processing in memory, a semester project, for example. This will be the first thing that we will ask you to read. It's a book chapter. We wrote it first in 2020, and good thing of archive is that we can, I mean, this is going to be published, as you see, as a book chapter, but the good thing is that we can even upload it in archive, and we can improve the work over time and update it with new things that appear, new works, and that's what we did very recently. So you can actually access now an updated version of it. So yeah, about memory-centric computing systems, we are going to talk a lot in the next few lectures. I'm going to stop here because I have to finish. I think it was a lot, 190 slides. It's quite good for 3 hours. We will, I mean, the slides are going to be available in the website. I mean, are already available in the website to you. So you can continue checking them. Can also watch the lecture from last year from Professor Mutlu, probably better than the one I delivered today, but along the same lines for sure. And you can indeed continue reading these slides. This is more motivation slides about this course, in this case about the famous RowHammer problem. But I think it's a very good to start, a very good place to stop, and we will continue tomorrow. Thank you, everyone, for your attention. Very nice to meet you. Yes,
Okay. But I recently I heard
Like the